for lab 7 is due on Wednesday. I made it due on Wednesday because I didn't put the link up early enough and because we had the previous deadline. But the lab report is going to be due on Monday. Monday is good.
There's no point postponing it.
Can you speak up?
There's no reason postponing it because we have a final exam on Friday, so we're going to have to study.
Yes.
Finish up the lab before.
That's what I think too, yes. Because otherwise it interferes. Should be a fun lab. I think it's one of the most, that one that turned out really well from my perspective. I'm really very proud of it. And it's usually easy to do. Not easy, but true. Did you learn something in the lab? Yeah,
yeah. Last lab is also pretty fun.
Last lab hard. That's hard for anybody, even conceptually hard. Now you have to turn your devices off. You're playing a game. Okay. Okay. Anything? So that is. What else do we have this week? Yeah, that's it. Huh? So go to the lab this week. Submit the lab report on Monday. The lecture stuff that we want to cover is DNS. Start today, and I want to cover IP multicast. Good.
Have we covered internet?
Have I covered the internet? I could not make a joke.
No,
that was a fill-in piece.
Okay.
Optional. Yeah, because I didn't want to start a new topic last week, and I was thinking that maybe it would get done too early. So I put this in. More informational. There was some more stuff.
The quiz, I guess?
Quiz. You got the email? Yes. What can I say? You know, the typo and the PA is just I didn't think. Yeah. I'm not going to get upset. I think they did a good job this semester, so I'm not saying anything to them. I need their help on the final.
Yeah.
So I'm grading the final with them. So I'm going to be present during all of the grading, which doesn't help them. Let's get started, huh? Something else about last week's lecture. We had this thing about the ICMP, a ping from inside the private network. Did somebody find out or look it up?
We already covered in the problem set.
What
it's part of problem set. So
okay.
that question, last question of the problem set.
So what was
8.
the answer?
So the NAT box use part of the sequence number to monitor the sequence number, record it, and keep a track on that of the ICMP message to match the response.
Yeah.
So
sequence number of what?
Of the ICMP message.
ICMP. The ICMP echo request message has a sequence number and an ID field.
And the ID field, yeah.
That is then used. Yeah. So okay, that's good. In an exam, this comes in an exam. If you don't know the solution, don't panic. Just apply common sense and say how you would do it. That's essentially the question. No one expects that you know exactly this answer, but that you come up with essentially what you need to do is you need to recognize that the regular mechanism does not work. Then you need to recognize that the key is to establish state information in the intermediate router, in the net router, and then you just have to then say which field it is. Yeah. Some of you have to then use your best judgment and it's your engineering principle. If you have to design it, how would you do it? That's essentially it's not that you can, memorize all these little protocols that you have to memorize all the protocols. All right, the DNS domain system. Okay, so what this is about is how to map names into IP addresses. The domain names for systems, they are alphanumeric. Neon, ECE, Toronto, www.google.com. These are called domain names. They have a certain structure, and the purpose of the structure is to aid in the mapping of this name into an IP address. There's another mapping going backwards done by the same system to go from an IP address to a domain system. And so the domain name system is essentially an internet-wide lookup directory, worldwide internet-wide directory that translates between domain names and IP addresses. And we can look at it like a distributed database, like a distributed lookup table. DNS is crucial, and you notice how crucial DNS is if your local DNS server is down. The local DNS is just one machine that is down. There should be a backup server or something that's also not working. If they go down, it's because the network to the DNS server is not reachable. Feels like the internet is disconnected, even though nothing is really wrong except one machine being down. It feels like this. Let's see, what else? So it's really crucial in the operation because nobody works with IP addresses. Everybody works with the WWs. Yeah, that's how people memorize addresses for the internet. I think most people don't know. Most people using the internet don't know what an IP address is, and they don't need to know. Yeah, kind of the same thing looking at a telephone system. People generally know what a telephone number is, and they can recognize structure. Even if you're calling a number, you have to know something about, if you're calling, you have to know something about the structure of the phone system, the phone number structure. You have to know what a local area, what an area code is. You have to know what a country code is. Dial 416. It's not 1416. So there's all these different rules, but none of that is required in the internet. They just can work with these very memorable names, www.google.com. Okay. Now, DNS, in the early days of the internet, so there was no domain name system. The mapping of machine names to IP addresses, this is when the internet had a few hundred hosts. That's it, not 200 hosts. But, so there was a single file, this is kind of interesting, that was kept by a research institute. That was the host.txt file. So text file that had for each computer on the internet, it had the IP address, the name, and the IP address for that name. That file still is running on the system, and you can put something in there. Actually, if you're writing a domain, this fixed mapping into the name is, I'm not sure if it's still called host.txt, but there is a file where you can write it, and whatever you write in there overwrites the DNS system. And you can give locally provide the mapping between domain names and IP addresses, so that whatever is in there will not call the DNS. Okay, so then and so what happened here with a single file that was kept on a computer, every so often you just had to download that file via FTP from this computer, and because that was the way to learn about new hosts. So each host has a complete list of IP addresses on the internet. That of course did not work very well for some time. So in 1985, actually quite early, the DNS system was created. Actually at that time, a few thousand hosts. Yeah, actually I can look this up. how many hosts we actually have, because that was one of the slides that I had on this internet lecture. Okay. Oh, here, look up. Got it. Yeah, it starts at 100 euros. Yeah. No. Okay. No, it's not. Okay. Oh, that's it. That's not. So 1985, I would estimate maybe 1,000 hosts on the internet. And that system is still running. More than 25 years later. Okay. This one you like? No. Okay, so we're getting back to that later on the details, but that's essentially how the DNS is organized from the local perspective. DNS is essentially a client-server protocol, where the client is called the resolver and the server is called the name server. These are the DNS name servers. The IP address of the DNS server is part of the IP configuration. You can learn it via DHCP. If not, you have to configure it by hand. So the way that it normally works is if your application program, let's say you're using a web browser, like HTTP, if it uses a host name like Neon TCP/IP Lab EDU, it calls the local DNS client. That's called the resolver. And the resolver then sends a query to the DNS server, and then with the name, with the host name, and the name server provides the IP address back. We will see that there is a little bit more to it, because the resolution is often, generally is done, requires multiple steps, and then there are, there's the question whether the multiple steps are performed by the resolver, by your local computer, or by the name server. Now that's the difference between a recursive and an iterative query. So this part here, the yellow part, is a DNS query. DNS messages most often use UDP for carrying the payload. But if the reply is very long, it uses TCP. So there's an allocated port, 56 or 57, reserved for the DNS server. So if you're using a name, you're calling the local resolver. The resolver is part of the client. So there is something running in the kernel of this operating system or your operating system that is the resolver. That performs the queries for all application programs. Resolver contacts the DNS server. DNS server returns the IP address. There's a reverse lookup also possible. You can come in with an IP address and ask for an IP. All right, and that's pretty much it. And there's actually a command interface that you can use. You can call DNS with a command. NSLOOKUP is one of the commands for a host. And that's something you can say, well, what's the name of www.ECE461Lec1128.ca. Okay, and so it comes. It comes back from the server with address 128.100.100.128. That's the U of T name server. And the answer that comes back, it is www.ECE461Toronto.ca is at IP address 128.100.131.143. It says something else is that this answer is non-authoritative. Authoritative, yeah? Pronounce it right? Good, thanks. Non-authoritative. That also means something. That we'll learn today or tomorrow. Okay. What other information do we get here? Okay. So let's learn a little bit about the structure of names. That's one thing. So the DNS names, they are based on DNS names are organized in a tree. That tree makes up the domain namespace. The names have nothing to do with location of the host. Completely disconnected from, there's some relationship to IP addresses and host names, but there doesn't need to be. Autonomous system numbers, it's done without regard to all of that. Okay, so that is principle. In practice, what you find is that all hosts with network prefix 128.100, and that's the U of T prefix, they all have the suffix utoronto.ca or toronto.edu. This is an interesting one. So let's do this. www.ECE461 Is doing the same thing? Alright. And this should also work. No. Huh? That cannot work. So what is going on here? It's Toronto. The computers at Toronto have multiple names that map into the same IP address. Yeah, so the toronto.edu and the utoronto.ca, they map to the same kind. They're both managed by the domain space allocated to U of T. Why is that so? What does .ca stand for?
Canada.
Canada, very good. What does edu stand for?
Education.
Education of what?
Of institution. Institution. Education institution.
As opposed to.
Institute.
Well, it is essentially
Public.
like if you're going to, let's say, universities in Great Britain. Yeah, if you're looking at that, then let's say you're going to, let's do this. Does not somebody know what the institution, education institution in Great Britain, how they end?
Cambridge.
So let's go. Give me a university, Cambridge University, Oxford University. Yeah. Oxford University. See this? .ac.uk, Academic United Kingdom. So .edu is a top-level domain that is allocated, is essentially referring to the higher learning institutions in the United States. Yeah, and so that's also the rationale between for having .edu is in Canada you're so close to the U.S. system. Somebody in the U.S. is looking for University of Toronto. They don't type CA. They would type Toronto EDU or UToronto EDU. And this is kind of interesting if you're looking at departments how departments in the university educate their publish their web address. Some of them go, if you go to, let's take ECE Toronto, yeah, University of Toronto. Okay, ECE.toronto.ca. Let's do computer science. Oh no, there you go. Oh, this is in. No, you see? TS Toronto.edu. kind of interesting. There's some institution want to appear more closer to the US. It's funny. Math does the same thing. So a couple of departments that do this. Anyway, so that's already interesting. To have these multiple mappings of domain names to the same IP address. So why do all, so addresses here, that's just because of their location. You get an IP address block, you get a domain name part of the hierarchy. If you're having a name server at U of T, that name server calls everything Toronto.ca or Toronto. This is the domain name hierarchy, the DNS hierarchy of domain names. Couple of things to know. It's completely hierarchical, a rooted tree. The root at the top is a period. Then below the root, you have then top-level domains. .org, .edu, .gov, .com. These are the top-level domains. They're called general top-level domains. There are other top-level domains that are country codes top-level domains. .ca would be a country code, specific country code top-level domain. EDU, just a general top-level, or generic top-level domain, not general, generic top-level. Then from there on, you subdivide further. You go to UCI EDU, Toronto EDU, Math Toronto EDU, ECE Toronto EDU, Neon ECE Toronto EDU. Yeah? So, and so what's happening here is this is the domain names, and what you normally have so what you have is that the top level, the administration of a part of the namespace is delegated by name servers to lower level name servers. That's how the hierarchy comes into place. So ECE Toronto EDU could now all create, the ECE department at University of Toronto could create subdomains. If it runs a name server, which I don't think it does, if it would, then it could create a domain called ECE Toronto EDU, and CE.ECE. So one for computer engineering and one for electrical engineering. And so it goes. So you could continue this an arbitrary number of times. What you have is that these days you essentially only have 2 or 3 of these delegation levels. The top level of the top level domains and the authority therefore over the entire domain space is held by the ICANN, it's the Internet Central Name Registration Authority. This is a non-government, non-for-profit corporation, which is dealing the highest authority for the administration of domain names, and they're also the ones who create new top-level domains. All right, so managed by UFT, managed by ECE. That's what it goes. You have these levels of delegation. So maybe let's go to fully qualified domain. Yeah, so the domain names, the full domain name is called a fully qualified domain name. There's 2 ways to write it. You can write it like CS Toronto EDU, or you can write it written with the hierarchy, with the top end of the hierarchy to the right. The difference between the 2 ways of writing it, this is how people normally write it. How name server write it is on the right hand side, where you have an additional period. That period indicates the root. So the root, that's pretty much it. And so if you're looking and editing the name allocation in a name server, you would also always have a period at the end. These substrings of a fully qualified domain names, they're called labels. Labels can have characters and numbers. And that's pretty much it. And there can be 63 character long. It's also allowed to have a dash in there, but other special characters are not allowed. So a dash is fine as a special character, but that's pretty much it. Let's see, very recently there was actually a change for, don't have it on my lecture, it just came to my mind. A change of that fully qualified domain names no longer have to be in Latin alphabet. Now you can now have any character set. So that is, of course, philosophically for the internet, that was a little bit of a leap of concept, because the internet has this world of a global community where everybody can communicate with everybody. If you know something is written in a letter code, something in Arabic that people who are not literate in cannot read, you no longer have that. At the same time, it's the internet, this concept that the internet is the infrastructure where everybody communicates. So this concept that the internet unifies the world and makes everybody communicate with everybody is conditioned on the fact that everybody speaks English pretty much, or writes in Latin characters, which is only a fraction of people. Anyways, so that's a very recent change. Was a long debate about that. All right, so the top level domains, there's these organizations, the GLDs. There is geographical. These are the country codes, like CA for Canada. There's one also for the United States. Even though that's not used a lot, it's used by government, some governments use it. For U.S. states, there's one like VA, which stands for Virginia, and so forth. So most of the world actually uses geographical top-level domains. Then there is the reverse domain. Reverse domain is done for the lookup. It's called the Internet Address ARPA domain. That is the branch that provides the reverse lookup, where you come in with an IP address and come in with an IP address and retrieve the domain name. These are these organizational domains. They play a big role in the United States, and their meaning is a little bit kind of what you have is .org is traditionally for non-for-profit organizations, but if the name is given out, nobody checks whether this is for non-profit, so we cannot trust that. .net for network organizations, also, companies use it sometimes. .mil is used by the U.S. military. .gov is used by U.S. government, federal government institutions. EDU education institution. .com is kind of the big. So that's how it was originally created. So now it comes with the, so we have this hierarchical domain name. Domains can have subdomains, subdomains can have further subdomains. The administration of names is performed by name servers. These are all name servers. The name servers are responsible for a part of for a contiguous part of the domain space, and they can delegate this further. Whatever they don't delegate, that is the piece that they are responsible for giving the ultimate response. These are the parts of the domain names that they are responsible for themselves. That piece is called a zone. It's called a zone. Zone is part of the subtree, and the DNS servers provide the authoritative replies 2 requests in their zone. It's a little bit subtle. The top of the hierarchy is a root server. The root server you have to find, like your domain, let's see, either your resolver, if your resolver only talks to the domain name server, then the DNS server has to then be able to walk, and clearly starts at the top and works its way down. First asking in this, you want to go for CS Toronto EDU, you first go to the root server, then you go to the, which then gives you the IP address of the EDU server, then you go there, then you get the IP address of the Toronto EDU server, and so you get then to the CS Toronto EDU server. Multiple steps. These steps can be performed either by the resolver or by the local name server. The root server is known, and the IP addresses of the root server is configured in all IP devices. So if you're having any Android, any PC, Windows, Mac, Linux, they all have a list of all the IP addresses of the root server. That's a bottleneck, yeah? So it turns out there are several root servers. They're duplicated. There are 13 root servers. So right now we have, so there's 13 root servers. The IP, they're located, and this is kind of the status here from 1998, that's some time ago. At that time, the root servers had still their original location. Very interesting. One in Japan, 4 on the US West Coast, 2 in Europe, the rest all around Washington, D.C. So these are the IP addresses that are configured. Now what one has is the IP, now what one has is the root servers now are duplicated in different pieces of the world. But a decision was made to not add additional IP addresses, to not add the configuration of systems. What happens is that the that identical root servers exist throughout the world, copies of them, with the same IP address. Did you get that? Maybe I should look something here on Wikipedia to look at. The slides should be there. But it's not. Root servers, DNS. Map of the network. Alright. This is the location of root servers today. You see the letters I, F, L, I don't know what the numbers 2, 3 are. Yep. The root server L, L, L exists in multiple places. Yeah, this is the root server L with the IP address 199.783.42. Let's go back here. Oh, that's the one where I have a typo. 198.32.64, was that the one? Let's maybe pick a different one where I have the full IP address. Root server F. 192.55.220. F. 199.552.21 and 241. Not the same.
Oh, it's the same. Yeah.
It is the same. Yeah. It is the same. I look now at a different server F. Let's go. This one here is operated in Pakistan. 192.552.41. So now we've learned about this internet, yeah? Internet, public IP addresses, everybody can have. Now at the roots, at the top of the name server hierarchy, all of a sudden, I mean, this is something that whenever you contact a new address by domain name, your local name server will contact the root server. So that's the address that is the most active. Now it turns out they're duplicated. So how is that done? How is the routing done? How do you know if you're here, if your root server F is somewhere in Venezuela or the Caribbean or in Pakistan or in southern France?
Doesn't matter.
How is that done?
It's basically the shortest path, and it doesn't matter which one you go to, because they all have the same information.
How's your routing done? You're doing a routing lookup. How is the routing done?
Shortest path.
What's your shortest path of what? I mean, the address comes from somewhere. It is propagated using a routing protocol. You're very close. It's not shortest path, but it is something of that sort. It has to do with routing. What happens, this gets information that is propagated by BGP. Now, the BGP policy rules are set so that what happens is that so all these addresses get propagated, so you get multiple path advertisements for this domain, for this autonomous system, and then you just pick the whatever the criteria is. So this is actually done using BGP. But it's bizarre. So these machines are heavily used. Why are there so many duplications? Well, these are the points of attack for the internet. Yeah, there was in the mid-1990s, late 1990s, there was a lot of concern about because at that time the pictures really looked like this. There was a high likelihood of attack and vulnerability was seen. And the way to solve this is just to have a machine spread out throughout the world. Yes?
Why aren't there any in Canada?
Why?
Why aren't there any in Canada? Why aren't there any name servers in Canada?
Maybe there's no need for it.
Like there's in Iceland and Pakistan, why not Canada? The second largest landmass.
So you look at this map here. Let's see. Let's look at this.
There's
that's Alaska.
I
there's
think
one in Toronto.
didn't you get one here?
Oh, FNJ.
Yes.
Oh, it's in Toronto.
That's good. I'm happy.
So there is one in Toronto. There are three in Toronto. There are three in Toronto.
Oh yeah.
Oh.
Multiple instances.
What about what?
I mean three servers.
Let's see. There are three of those
JL.
in Toronto. There is the F, the J, and the L. You see at this.
Yep.
Internet system.
We could try to find out whether there's probably is one in Front Street, one of them is probably close to the TSX, because there's a lot of close to the financial market. Yes.
So all those FJ and Ls, they all have the same information, right?
Well, they don't have so much because the root servers have to be able to. They have to know the location, meaning the IP address, of all top-level domain servers.
Yeah.
But normally what's happening is that the root servers are also then handling the top-level domain requests. Yeah. So, but in principle, the function of the root server is just to find out the top-level domains. So, kind of how many top-level domains there may be maybe 500 or so, several hundred. My slide says 200. I think that's low, because there are 200 countries.
I'm just saying that we know all the name servers as the name as J all contain the same information, right?
Yes, they all have all name servers have the same information across the different letters. Yeah, so the names are what you can see here. Look at this. Name. The name here is. The resolution that we show. You see here, this one is ICANN, the other one was VeriSign, and these were the IP addresses here. You see here that J is operated by RIVE, NCC, Network Consortium, and NIC, that is VeriSign. The network used to be the Network Internet Corporation. Yes.
These root servers IPv4 and that's the public address, right?
These are all only public addresses. There is no mapping of private IP addresses.
So when you duplicate a system, don't you have a conflict in IP address?
Yeah, that's what we discussed. It's resolved by routing, because each of these DNS servers is part. You know, it's in a subnet. They essentially propagate the network that they're in. The prefix that where the server is located. The prefix. So this one here is 202.12.27.33. So probably prefix 202.12.27/.0/24 is propagated from various directions. Everybody who is an en route server. These autonomous systems, they are sending BGP information, advertising that route. Now, it's possible you get multiple advertisements, you pick one. So you always get one, and in all likelihood, it's the one that is closest to you. It's a very nice implementation of what is called anycasting, but we'll get to that later. Yes?
Let's say there's some sort of transaction, right, that is going on between a host who wants to know exact IP addresses from other hosts. So it contacts the name server in Canada, right? And then the request gets into name server 1, right? And in some other instance, let's say the host needs something else, right? If it goes to another server, it's going to still work out, right? If a request
it should work out. I mean, the reason that you'll have kind of this geographical distribution is a lack of trust that is there. On a global scale, yeah. So some of these countries are not peaceful with one another, and so what you have is that they don't want to have. I'm not doing this very well. So there's a matter of trust between countries at a kind of information security level, that one does not want to be subject to somebody playing with, let's suppose in China the militaries would have military domain names, therefore .mil.cn, and the name resolution is at the server is at the Pentagon. In the US, and so it's just the issue of who resolves the name. You can then say, well, that server is, here's the IP address of, the mil.cn server, and it is a computer in the Pentagon, and saying, give me your password. Yeah, so, but, I mean, these are caricature, but similar. These considerations play a role. So that's the reason. But it should work. Yeah, it should work. This function they perform is very simple. The only thing that is critical about it is that almost any interactions using the internet require the involvement of the root server. So that the subfunction itself is almost primitive. Yes.
I'm just wondering who pays for all the DNS servers. I mean, they are very global infrastructure, and I'm just wondering who pays for them.
Let's see. They are run by they are run by companies. NetNod, Formula Autonomica. I click on ICANN. This is the internet. This is the top organization that is governing the namespace of the internet. I believe ownership here is almost symbolic. It's probably that this is government funded by the government of Nepal. That would be my estimate, because ICANN itself does not make money. It is actually dependent on donations. Yes.
I noticed it says the type server. Sometimes it's global, sometimes it's local. Is that the root server?
That I do not know. I don't know if that is if this is an official designation or not. But what you see here, they have the autonomous system number. So that is actually quite interesting. If we go on here to Saudi Arabia, the same autonomous system number. Is that funny? So that's how this works. It's using BGP. Yeah, the same autonomous system located around the world. Yeah, whoever gets the advertisement, if you're getting an advertisement from Saudi Arabia, then if your routers get it, then that's where the traffic will go. And they are run by the same organization, but I don't know about the business structure here, but I believe the DNS is really a global service that is essential for the internet to run. It's something at the level of peering, at the top level. These places have to be, these pieces have to run for the internet to work. And so the only issue that is in place is trust. Trust and security against hacking. I mean, this is a protocol designed in the 1980s. You can imagine that it does not have any, we know this by now, again, there's no security really. Even though there are extensions to add secure hashes, digital signatures, to DNS names, that is done, but it's not widely used. Yeah, to the degree that let's see, maybe some of you have this. I have it. My service, network service provider, at one time switched to what is called an open DNS server. They switched the DNS server to a particular system, to a particular DNS service, which filters for suspicious resolution. Anyway, so we discuss the second part of DNS tomorrow morning. So what we want to go through is the structure of zones and domains, and then just look at the details of iterative and first clear.